system, devising schemes to drill through the icy outer layers of Europa, sending semi-autonomous probes into the metallic hydrogen inferno of Jupiter, skipping through the storms of Saturn, and more. And so after proving its worth, its ingenuity and its patience, Batuta had finally been permitted to exit the gates of the solar system in the full knowledge that the worst was yet to come. As it considered the sacrifices of the heroic probes that had come before it, the Cassini, the Huygens, the Juno, its curious mind turned to their predecessors, launched by NASA decades before, who had gone even further. Far beyond Jupiter, far beyond Saturn, far beyond the outer worlds altogether. For as strange and extreme as our own solar system is, we are not, by far, the strangest of systems out there. There are even weirder, more dangerous places. But to get to them, to explore their beauty and understand their secrets, Batuta would first have to travel the great gulfs between the stars. After only a few decades of cruising, Batuta had finally reached the long-established threshold. The heliopause, the boundary between the solar wind and the interstellar medium, a feat first achieved in ages past by the Voyager 1 probe in the opening years of the 21st century. Batuta could hear the ancient greetings etched in the famous Golden Record, a compilation of voices, languages, sounds and music of planet Earth, hastily assembled in August 1977 just before the probe's launch by the legendary scientist and science communicator Carl Sagan and his collaborators. Indeed, the designers of this mission understood its significance. The probe would, decades after launch, become the first human-made craft to enter interstellar space. Musing on Sagan's words at the time, Batuta considered its own mission as it passed this remarkable milestone. Perhaps the records will never be intercepted. Perhaps no one in 5 billion years will ever come upon them. In 5 billion years, all human beings would have become extinct or evolved into other beings. None of our artifacts would have survived on Earth, the continents would have become unrecognizably altered or destroyed, and the evolution of the sun would have burned the Earth to a crisp or reduced it to a whirl of atoms. Far from home, untouched by these remote events, the Voyagers, bearing the memories of a world that is no more, will fly on. However, the mission had almost ended in disaster. Early in its journey, Voyager 1's scan platform jammed, removing the probe's ability to orient itself in space. Luckily, engineers were able to fix the issue by waggling the scan platform back and forth. But for years, during its outward cruise, they worried and fretted that all their efforts would be for naught. The mission, however, was a roaring success. Along with its twin, Voyager 2, humanity got its first close-up, high-res view of the outer planets, and that lonely probe, now long since lost to the infinite blackness of the space between the stars, was but the first of many. And it took advantage of a unique alignment in the solar system, when all the giant worlds happened to be all along roughly a straight line. By carefully arranging its trajectory in a trick known as the gravitational slingshot, the spacecraft was able to steal some of the momentum of the giants for itself, giving it more than enough speed to escape the sun's gravity permanently. After that, it was left to its own devices as it cruised through the galaxy, orbiting its center, just like every other star. But Batuta had other ideas. It was aimed in a general direction, but had not yet decided its first target. There were so many to choose from. Indeed, it had more than enough time to decide. The passage through the outskirts of the solar system would take several thousand years. And so Batuta busied itself with another task. It fashioned a thin metallic wire and unspooled it behind the spacecraft until it reached a length of 1,000 kilometers. It was a long, but simple, antenna. And through it, Batuta listened to the cosmos. It heard the groans of giant molecular clouds, screams of stars torn apart by black holes, the subtle whirring of the Milky Way's magnetic field, the drumbeat of distant pulsars. Sometimes placid and sometimes riotous, picked up a universal symphony, the perfect background music for the first leg of its journey. And it was through similar means that we knew when Voyager 1 had become the first ever human-made object to pass into interstellar space. For while the Sun's gravity extends for well over a light-year, and objects still maintain feeble orbits at that distance, there really is a measurable distinction at the edge. And we know this because of the behavior of plasma. Normally we associate plasmas with dense, hot environments, like a bolt of lightning at the surface of the Sun. However, in the outer depths of the solar system, the plasma environment is still hot, but incredibly thin. This plasma environment around the Sun is dominated by its solar wind. The entire solar system sits in a bath of these particles. But eventually, the solar wind slows down enough that it cannot sustain itself against the interstellar medium, and this supersonic flow comes to an abrupt and untidy halt. This boundary is known as the termination shock, and magnetic measurements from Voyager 1's antenna indicated that it encountered this boundary when it was at a distance of 94 astronomical units from the Sun, 1 astronomical unit being the equivalent of the distance from the Sun to the Earth. Past the termination shock is a region known as the heliosheath, where the solar wind slows down and begins mixing with the interstellar medium. And the outermost layer of that region, the border with true interstellar space, is the heliopause. Voyager 1 reached this boundary on August the 25th, 2012, at an incredible 18 billion kilometers from the Sun. And there it found that interstellar space is different. For the Sun's solar wind and giant magnetic field shield the solar system and its inhabitants from the toxic environment beyond. The toxicity brought about by the presence of deadly, interstellar, cosmic rays. And to understand cosmic rays and what they mean for our survival on the Earth, we have to go back to 1912 and an Austrian physicist named Victor Hess. In the 19th century, scientists had discovered that air was seemingly being ionized by excess radiation, radiation of which they simply couldn't pinpoint the source. It had been believed that this radiation had been coming from the Earth, from the ground beneath our feet. And so, measurements had been taking place at higher and higher altitudes to test this idea. Far exceeding the height of an experiment a couple of years before on top of the Eiffel Tower, Hess had used a hot air balloon to travel a kilometre up into the sky. He then followed this experiment by ascending in his balloon to a height of 5 kilometres, but with one key difference. He performed his experiment during an eclipse. He saw no major difference in the quantity of radiation. Both the Earth and Sun consequently eliminated as the cause. The results were clear and earned him a Nobel Prize in 1936. He had pinpointed a source of radiation coming from space. Just about every high-energy process in the universe creates cosmic rays. Some are created near the surface of the Sun, others come from distant supernovae, still others from quasars or magnetars or hypernovae. But because cosmic rays are charged particles, they can be deflected and reflected by magnetic fields. Thus our Sun provides a protective bubble around the entire solar system, and the Earth's field provides another line of defense for surface dwellers against these cosmic threats. But the defense is not total. High-energy particles encounter a typical human body roughly once every second. While most of them just harmlessly pass through, sometimes they strike a strand of DNA, or oxidize a random molecule in a cell. If the damage done is left uncorrected, it can turn into a replication error, resulting in the growth of a cancer. Indeed, in 2023, Voyager 1 went silent for 5 months, possibly as a result of cosmic rays interacting with its computer. And these dangers get even worse beyond the heliopause, where not even the sun can offer its protection. But despite this, there are still objects here. Lonely denizens whose only knowledge of the sun is that of a prick of light, a star slightly brighter than the others. Young man, I'm afraid you are wasting your time. If there were any more planets, they would have been found long before this. In later years, astronomer Clyde Tombaugh would recall being told this in 1929, the year before he discovered Pluto. Pluto was at the time the most distant known object orbiting the Sun, and Tombaugh only saw it as a faint dot of light, betraying its existence as a planet only through its subtle movements against the background of stars. But over the decades, many astronomers hypothesized that Pluto was not alone, that there might be an entire population of objects, planet-sized and otherwise, in the fringes of the solar system. And it wasn't until 1992 that this hypothesis was confirmed, when a pair of astronomers, David Jewett and his graduate student-turned-collaborator Jane Liu, after half a decade of painstaking searches, found a companion to Pluto. The object would soon get a name, 15760 Albion, and it has since been joined by thousands of others in a population known as trans-Neptunian objects, TNOs, which stretch from roughly 30 astronomical units to an orbital distance of hundreds of thousands of astronomical units. This population, with subregions known as the Kuiper Belt and Scattered Disk, is the home of comets that make regular frequent visits to the inner solar system, like the famous Halley's Comet. While these regions have a few larger members, Pluto, Sedna, Haumea, Makemake and others, the vast majority of trans-Neptunian objects are small objects made of frozen volatiles, like water, ammonia, and nitrogen. Little is known today about the populations of the trans-Neptunian